Greetings for the day. Myself, Ayyappan Subramanian, and I'm here to present the paper titled Caveat IoT Emptor Towards Transparency of IoT Device Presence as part of the course INSE 6170 Network Security Architecture and Management. This is the agenda for the today's presentation. We'll start from the introduction, which discusses about IoT and its security. Following that, we discuss the existing techniques that are related to our problem statement. And then PISA protocol will be discussed in detail with its design overview, implementation, trusted softwares on IoT devices, and reception application. And during the end phase of the presentation, the evaluation of the protocol along with its limitation are also discussed. In this digital world, we want to make everything smart. And to make it smart, it needs IoT in play. The rise of IoT in daily life has led to interconnected devices that automate tasks, improve efficiency, and enhance convenience, from smart home system to smart watch, which act like wearable health trackers. Making everything smart is pretty cool. However, in the aspect of cybersecurity, wherever there's IoT, there's a concern for security. The connectivity of IoT devices allows for real-time data collection and personalized experiences, but it also raises concerns about security and privacy. So now the Internet of Things has seamlessly integrated into our lives, yet the risk of hidden devices collecting data is a growing concern. With GDPR and CCPA emphasizing users' privacy, there's an urgent need for solution that informs user about IoT presence. A lot of techniques has been proposed to increase the transparency between the IoT device and the user device. Some of them include the end-to-end encryption, authentication, and other cryptographic constructs to secure IoT devices. And some other includes protecting sensitive data from passive in-network adversaries by analyzing metadata of network traffic. And some other methods to mitigate the risks are like traffic analysis to monitor data flows, or specialized hardware to detect devices which are not fully effective. So though a lot of researchers and techniques are proposed, device manufacturers rarely adopt security research in their products, and current IoT security guidelines mostly ignore user privacy. These guidelines target device owners, but IoT devices affect everyone nearby by sensing and controlling the surroundings. Ideally, there should be a way to inform people about IoT device presence, capabilities, and activities so they can make informed choices. So when I say we need to inform people about IoT device present, this is where the idea of this paper comes into discussion on specifying the way to inform people about IoT device presence. To discuss about the core idea, design, and implementation of this paper, first let's understand what is snooping and actuation is. So snooping refers to the ability of hidden IoT devices to monitor and collect data about nearby users without their knowledge or consent. And what actuation means is the ability of IoT devices to take actions in the physical world based on the data they collect or the commands they receive. So these are the two terms which we need to know, and snooping refers to the privacy concern and the actuation refers to the safety concern. So these are the two major concerns when it comes to the transparency. So in order to increase the transparency and to tackle the safety concern and the privacy concern which we discussed just before, this paper constructs a privacy agile root of trust architecture for IoT devices called PISA, Privacy Agile IoT Sensing and Actuation, which mainly focus and address on snooping and actuation, which are considered to be the privacy concern and security concern on using IoT devices. So this PISA has two components. One on the IoT device that gives periodic announcement of its presence, other on the user device which captures and processes the announcements. And to mention here about the PISA protocol, there are three main advantages that I want to mention here. PISA requires no hardware modification. It uses a popular off-the-shelf trusted execution environment TEE ARM trust zone and guarantees announcement of its presence even if all device software is compromised. And this protocol mainly targets the IoT device which are resource limited with strict cost and energy constraints. So before deep diving into the PISA protocol, let's understand some of the terms which are part of its background like TEE, remote attestation, etc. So starting from TEE, ARM Trust Zone M creates a trusted execution environment by partitioning hardware into secure and normal regions. The secure region holds trusted code and data, while the normal region houses user programs. Trusted Zone EM enforces isolation so non-secure code cannot access secure memory. It also features secure boot, which verifies the integrity of trusted code at startup, and non-secure callable functions, allowing controlled access between regions. So these are the key features of Trust Zone M. So moving on to the peripheral security, through the Trust Zone Security Controller TZSC, peripherals can be locked in the secure region and security violations trigger secure fault exceptions which are safely handled. And this setup ensures confidentiality and integrity for critical data and code. So, and that's the reason why it is considered as a background for this PISA protocol. So another background which we need to discuss is as follows. So the remote attestation RA is a security service that detects malware on a remote device by allowing a trusted verifier to measure the software running on it. RA uses a challenge response protocol. First, the verifier sends a challenge to the device. Then the device computes an integrity check on its software and returns the result. And finally, the verifier checks this result to confirm the device integrity. So the challenge response protocol consists of three phases: request, response, and verification as stated in the presentation. And the integrity check can use a message authentication code MAC or a digital signature depending on the device. So usually low-end MCUs typically use MACs with a shared symmetric key, and high-end TEE use digital signatures with private public key pairs. So that's what it is with respect to the integrity check. And in PISA, remote attestation ensures that devices operate securely, leveraging Trust Zone M to perform attestation locally and report results using signatures similar to advanced system. So these are the two main concepts, TEE and the remote attestation, which are considered to be the core background of the PISA protocol. So after the background, let's move on to the design overview of the PISA protocol. So the PISA protocol has three entities: IDEV, which is IoT device, UDEV, which is user device, and MSVR, which is manufacturer server. So let's look into it one by one. So IDEV, this is a resource limited IoT device equipped with a trusted execution environment. It's deployed in public spaces like airports or stores or semi-private spaces like hotel rooms, etc. And following that, we have UDEV, which is user device. This is the user's trusted device, which is assumed to be within network range of IoT device, and it has an app that receives and verifies announcement from PISA. So we have a separate section for reception app. We will be looking in depth uh, in the upcoming slides. And MSVR, manufacturer server, the manufacturer server, which is powerful and secure, provisions IoT device at production time and maintains trusted backend support. So these are the three main entities of the PISA protocol. And moving on further, we have two software modules in PISA protocol. One is announcement and the other one is reception. So in PISA, announcements are handled by a trusted module on IoT device, which is housed in a trusted execution environment TEE. This module ensures that IoT device broadcasts announcement periodically, regardless of any software compromise. The announcement includes a fresh timestamp, a device description, and a signature authenticating the packet's origin. So the figure below shows the example of announcement message. The frame body consists of MAC header, SSID of PISA, which is considered to be a mandatory field, and we also have vendor specific elements, which includes the announcement bytes as well. The announcement comprises of 128 bytes. The 128 bytes of announcement includes nuance, timestamp, signature, URL, URL length, and attestation report as well. So following the announcement module, the next software module is the reception module on the user's side. So UDEV, user dev device reception module captures these announcements and validates the timestamp and signature and provides user with information on the presence and functionality of IoT device. So typically, like to be precise, the announcement of IoT device initiates the announcement, and the reception module captures the announcement via the same network, and it processes, like it verifies the signature, the authenticity, and once all the verifications has been done, the it gets the details of the information and functionality of the IoT device. So that's what it is in precise. And when it comes to this design overview, we have the design requirement and challenges as well. So the main design specification and challenges here is the low latency of announcement and low bandwidth of announcement. So announcement must be fast with minimal impact on IoT device normal operation, and it should be of low bandwidth. Announcement must consume minimal bandwidth. So both the cases is to reduce the latency and to reduce the network capacity as well. So, and the other thing is bandwidth of message announcement. So since broadcast message are subject to size constraint and has the potential to impact network efficiency and transmission capacity, regardless of the network type, it is important to optimize the announcement message. So the announcement message is usually defined as MSGANNO, as you see in the slide. So the announcement message only includes a URL to manifest of IoT device, a timestamp, and a signature. And the user device verifies announcement messages fetched from manifest of IoT device via URL, ensuring efficiency and authenticity. So these are considered to be major design requirement and challenges that are need to be considered while you design the PISA protocol. So following the software module of the PISA protocol, let's look into how the PISA protocol is designed and how the flow looks like. So the PISA protocol mainly includes three phases: the registration phase, boot time phase, and the runtime phase. So let's look into it one by one. So firstly, the registration phase. So during registration, MSVR, that is manufacturer server, generates manifest IDEV with a detailed device profile and shortened URL, which is mentioned as URL man for efficient retrieval. So, and then in provisioning, the MSVR installs required software set up secure configuration, and certifies a public key for encrypted communication. So as I mentioned, the install software, as I mentioned, install required software, it installs swdev and swpisa as stated in the presentation, and manifest idev is updated for any software or vendor change, ensuring ongoing trust though through MSVR signature or an external CA, reinforcing PISA's security framework. In addition to these, URL manful is included in manifest IDEF so that the user device, when it later uses URL man, can detect if the redirection is wrong. And also for sanity purpose, this MSVR can include a status flag in manifest IDEF to indicate if IoT device is revoked. So after the registration phase, we have the boot time phase. So in the boot time phase, we have something called time sync protocol, which plays a very significant role. So the time sync is critical in PISA to prevent replay attacks, keeping IoT device time accurate by syncing with manufacturer server. So as I said before, the entire process is like we have an announcement getting triggered, and it is received by the application, and it is processed for the verification, and then it retrieves the details. So without proper time synchronization with the manufacturer server, it is easy for the attackers to do replay attack. So that's why I said that the time sync protocol plays a very significant role in preventing the replay attack. And further, we have process flow. The So let's understand how the protocol works in the process flow. So the IoT device requests a timestamp, which is called sync rec, request, and the manufacturer server verifies the sync request with public key of IoT device and replies back with sync response with timestamp, and following that IoT device confirms with sync acknowledgement. So typically it takes like it's more like a three-way handshake where you have a synchronization request, and the MSR verifies the IoT device with the public key, and it responds back with the timestamp, and once it is received, the IoT device acknowledges back. And as timers may drift, regular synchronization helps IoT device stay aligned with manufacturer server's time, so ensuring the time accuracy. So as I said before, since it is a significant factor, we need to regularly synchronize the time so that it can be accurately matched with the MSVR's time. So following the boot time phase, we have the runtime phase, and PISA currently uses a push model where IoT device periodically sends announcement message, keeping the user device updated. We also have a pull model where the user device initiates the communication similar to Wi-Fi's AP discovery. And the PISA runtime phases has two phases, like the announcement and the reception. So the announcement phase, the IoT device performs attestation and announces the message with timestamp, nuance, URL man, and the attestation report. And whereas in the reception phase, the user device validates the announcement message or message freshness and checks for its trustworthiness. As I said before, like it goes on for the verification and checks the integrity through the attestation report. And we also have something called attestation and announcement. So in the attestation and announcement, when T attest and T announce align, the IoT device attests and announce sequentially for the latest security status. So this allows flexible timing to prioritize essential functions on low resource devices. So we had a very detailed discussion about the design and its flow of the PISA protocol. So now let's look into the implementation of the PISA protocol. So the implementation setup of the PISA architecture involves several key components. So let's look into it one by one. So first one is the hardware platform. So the PISA architecture is implemented on this microcontroller ARM Cortex M33, which supports Trust Zone M, a trusted execution environment that provides a secure area for executing sensitive code. And the TEE, trusted execution code, which we discussed briefly in the background. So this hardware enforced component isolates trusted code and data from untrusted software, ensuring the integrity and confidentiality of the PISA system. And the next thing we have is secure peripheral. So that involves CTIMER2 and UART4. So these peripherals are configured as secure, meaning only the trusted computing base can access them. So this configuration is enforced by the trusted zone hardware, which raises a secure fault if unauthorized access is attempted. And the next one is announcement mechanism. So the PISA uses IEEE 802.11 Wi-Fi beacon frames to broadcast announcements about the device presence. So this method allows for communication without requiring a direct connection to a network. So following that, we have a message structure. The announcement message includes a fresh timestamp, a description of the device, example, sensors and actuators, and a signature to authenticate the message origin. And we have handling secure faults. So the system is designed to reset the MCU if a secure fault is detected, ensuring that the device can continue to operate and broadcast announcement even under attack. And for the performance consideration, the secure timer is given the highest priority to ensure that announcements are made in a timely manner with minimal impact on the device normal operation. And finally, we have the message limitations. The size of the announcement message is limited to 255 bytes due to the constraints of the beacon frame format, necessitating efficient use of space within the message. So we have discussed the implementation setup, and following that we have trusted software on IoT device. So it has three things to discuss. The first one is non-secure application in normal region. So the non-secure application operates in the normal region of the IoT device, performing general tasks such as continuously reading temperature data from sensors, and this data is then transmitted to an external server via the network interface. Access to sensitive resource is managed through a secure stub, which serves as a controlled gateway prioritizing PISA announcement to ensure that critical security communications are not delayed. The application depends on the trusted execution environment for secure data transmission, ensuring that all information sent to external servers is both encrypted and authenticated, thus maintaining its integrity and confidentiality. And following that, we have PISA Trusted Computing Base TCB in secure region. So the PISA Trusted Computing Base operates within the secure region of TEE, utilizing the ARM Trust Zone M architecture to create a robust security framework. The TCP manages critical security functions such as local attestation, secure boot, and the execution of trusted applications. It ensures that only verified code runs on the device, preventing unauthorized modifications. Through local attestation, the TCP generates a report that confirms the device state and authenticity of its software, establishing trust with external entities like user devices and cloud services. And additionally, the TCP manages secure timers and schedules periodic announcements, ensuring reliable communication even if software is compromised. So this trusted computing base is responsible for a reliable communication even if software is compromised. So I just want to underline this word. And following that, we have network stack. So the network stack is crucial for managing communication protocols and facilitating secure data transmission. It operates alongside the TEE to guarantee that all communications are both secure and authenticated. The stack implements various protocols for data encryption and integrity checks such as TLS or SSL to protect data in transit. It is designed to handle both incoming and outgoing data securely, ensuring that transmitted information is encrypted and that any received data meets known security parameters. By isolating the network stack from non-secure applications, the architecture minimizes exposure to potential threats, enhancing the overall security of the IoT device. So these are the points that need to be covered for the trusted software on IoT devices. So previously I mentioned we will be discussing about the reception app in detail. So this is where the place it is. So we have the reception app. The reception app is an Android application designed for devices such as the Google Pixel, etc. Like all the Android devices as it states, and its primary function is to scan for and interpret Wi-Fi beacon frames that carry announcements from IoT devices equipped with the PISA architecture. This enhances user awareness about nearby IoT devices, informing them of their presence, types, and capabilities. So let's look into the key functionalities of reception app. So the first one is permission and setup. So the app requires specific permission for optimal functionality. So it requires access, find location, and change Wi-Fi state permissions. And furthermore, like we have scanning for beacon frames, the app utilizes the get scanned result API from the wi-fi.scan result library to scan for Wi-Fi beacon frames, which are periodically broadcasted by PISA compliant IoT devices. It listens for Wi-Fi signals and filter for those containing the SSID PISA, identifying them as a PISA announcements. And parsing announcement data is the next phase, and upon detecting a beacon frame, the app extracts vendor specific elements using the Marshall API from the os.parcel API, os.parcel library, and this data includes the announcement message and a manifest detailing the IoT device capability and functionalities. And obviously we need to verify the signature. So the verification of signature is also done. The app performs signature verification on both announcement message and manifest using their corresponding public keys. And finally we have user information display. So after successful verification, the app presents the device description and the attestation report on the user device screen, including details about the IoT device and capabilities. Till now we have discussed the implementation and the flow of the PISA protocol. Now it's time for the evaluation. So we have different kinds of evaluation like the IoT device performance, user device performance, etc. So for the IoT device performance, the average boot time is 1300 milliseconds, and we have the latency factors, the time synchronization. The time sync includes network delay, two signing operations, and one verification operation. So these are the latency factors. And similarly for the user device performance, the time taken is 1070 milliseconds, and we have some of the latency reasons like network delays, context switching, etc, etc. And to discuss about the manufacturer server performance, so the average time is 5.6 milliseconds with a standard deviation of 2.77 milliseconds, and this process includes one signing task, two verification tasks, which can be efficiently done in parallel for multiple devices. And for the data size, the size of the manifest IDEF can range from a few kilobytes to hundreds of kilobytes, with 2857 bytes used for testing. The TCB size is 184 KB on the NXP board and 682 KB on the ESP32 board. This size includes the necessary software and a network driver which have been optimized to remove any unnecessary paths to reduce potential risks. The discussion and limitation of the PISA protocol includes runtime overhead. The paper highlights how announcement frequency affects CPU usage. So for example, an interval of 1 second leads to 80% of CPU utilization, which harms application performance. However, a long interval of 100 seconds raises a utilization of 99.7%. And for the CPU utilization calculation, it is given as T normal divided by T normal plus T announce into T normal. So that's what the CPU utilization is calculated, and we have TCP oversize. So increased attack surface, a larger trusted computing base increase the attack surface, potentially introducing vulnerabilities. So I think that's one of the limitation, and to mitigate this, PISA minimizes the network module to only necessary components, utilizing a UDP driver for essential functions and excluding unnecessary protocols like TCP and UDP. So the further things are compatibility and secure updates. PISA is designed to work across various network interfaces like Wi-Fi and Bluetooth, allowing it to adapt to different environment, and it supports payloads that fits in announcement size and implements a secure update mechanism where updates are authorized and verified to ensure security. And to talk about user privacy and network security, to maintain privacy, PISA uses anonymous methods for manifest retrieval such as Tor and peer-to-peer networks. And to discuss about the role of MSVR, it is crucial for managing time sync and device manifest database, as we all know. And if overloaded, certified third-party servers can help by handling some requests, ensuring both scalability and security within the PISA framework. So finally, we are in the conclusion part. In summary, the PISA architecture represents a significant advancement in the design of privacy agile IoT devices. By implementing a systemic approach to periodic announcement, we can enhance user awareness while maintaining robust security, and the use of TEE ensures that these communications are both secure and trustworthy. And as we discussed before, the performance evaluation is also done, and as IoT device continues to proliferate, solutions like PISA will be crucial in addressing privacy concerns, ensuring that users remain informed about the devices in their vicinity. So these are some of the references that I used for this presentation. You can have a look on this, and thank you for watching.